Hello, everyone. Welcome to the Reinforcement Learning Reading Club. In this session, Mohammadreza Nakhaei will present this paper from 2021. And Mohammadreza is starting his PhD in Aalto Robot Learning Lab in the next few months. So, Mohammadreza, you can begin.
Yes, of course. Hello, everyone. At first, I want to thank everybody for attending this session and listening to my talk on the paper titled Improved Learning of Role Manipulation Tasks by Tactile Intrinsic Motivation. This paper was published in April 2021 and authors are from ETH University in Zurich. Let's begin. At first, I want to talk about the motivation behind this paper. As you may know, conventional oral algorithms such as DQN, DDPG, PPO, to name only a few, when the reward is sparse, usually they perform weakly. And for example, if the agent received the reward at the last time step, or if the reward only indicates if the agent was successful or not. In these settings, the performance is not great, mainly because of exploration is really hard in these settings. On the other hand, designing reward functions can be challenging in reinforcement learning, especially in the field of robotics. Because in many robotic tasks, it contains several stages and designing reward function for the whole task is difficult. And sometimes it can actually lead to unintended behavior. Intrinsic motivation, especially intrinsic rewards, can help the agent by encouraging the agent to improve novel areas, in areas where the agent thinks that the agents believe that it may contain valuable information. This intrinsic reward can lead to better performance, especially if the reward is sparse, because in this kind of setting, as I mentioned earlier, exploration plays a more important role and it's more important. Therefore, by shaping a reward function which is based on the states of the systems and the learning progress of the agent, the performance can be improved. If you consider humans, especially babies, they explore the environment and tries to learn about different objects, for example, their shapes, their properties, by touching. And inspired from this behavior, authors of this paper propose using force sensor measurements for intrinsic reward. Well, at first I want to talk a little about the history of intrinsic reward and some important kind of it. The first category is state novelty, which is also known as visitation count. In this kind of intrinsic reward, the intrinsic reward is actually inversely proportional to the number of times a state has been visited. For the continuous state space, they use usually pseudo count. And one solution to this problem is using density model, which returns the probability of observing the states. In this kind of intrinsic reward, the motivation is that the agent should be encouraged to search for states and areas where it hasn't been visited. And the agent is rewarded if the agent sees something new. It experience something new is a better definition. Another type is using prediction error instead of state novelty for intrinsic reward, and actually this method is more scalable. In this kind of intrinsic reward, the agent learns to predict something, usually the model of the environment, the dynamic model, and as the agents get better at learning the model, the intrinsic reward reduce. And when the intrinsic reward is high, it means that the agent hasn't explored that area, and therefore exploring that area could be beneficial for the agent. As you can see from this equation, intrinsic reward is proportional to the prediction error, and instead of using a state space, we can use a feature space. Because in some environment, especially when images are used, a state space has high dimensions, and using this error is not is computationally inefficient, and it does not contain valuable information about the environment. So a function is used to encode a state space into a set of feature space. This feature space should be compact, it should have a low dimensionality, and it should be sufficient. It means that it should contain enough information about the model. And finally, it should be stationary so that the agent could learn and actually could use this function for so that it could learn the model of the environment. Some of the choices for G function are identity function when the state space is low and does not have, and the dimensions are not large. Another choice is random features. In random features, a model, usually a neural network with fixed parameters are used. For example, in an image state space, consider a convolutional neural network with fixed weights. In the output, there are a set of variables with a set of continuous variables, and the state space is encoded to those continuous variables which has lower dimensions. Another option is using variational autoencoders, which are an unsupervised learning method used for reducing the dimensionality of states. There are other forms of prediction error. For example, instead of predicting and learning the forward dynamic model, we can use inverse dynamic model. In inverse dynamic model, given the state and the next states, the model tries to predict the action required for this transaction. Another option is using random network distillation. In this kind, two neural networks or two models are used. In one model, the parameters, the weights of the neural network is fixed, and the other will predict the output, and it is learned to imitate the first network. The intrinsic reward is proportional to the error. Finally, another type of intrinsic reward is using information gain, which is usually based on reduction of uncertainty. We can, for some type of this is using Bayesian surprise and learning progress. It encourages the agents toward areas where it doesn't know, and it will explore the areas so that it could reduce the uncertainty of the model. This type of intrinsic reward has an advantage. There's a problem in intrinsic reward called TV blinking noise. I think in a paper called Larger Scale Study of Intrinsic Motivated Learning, the authors proposed using only intrinsic reward, and they totally disregard the extrinsic reward. In an environment, they modified one environment, actually one video game, and the agent was able to push a button, and every time it pushed, a new picture will appear. In when they used prediction error, because the image was, every time it was something new, the agent actually got stuck there and didn't improve at all. But this type of intrinsic reward can solve this problem because this noise does not reduce uncertainty of the model. So it can deal with this problem. Now I want to talk a little about goal conditioned reinforcement learning. The NDP form consists of a state, action, goal, reward, and transition. The distribution of the initial states, and discount factor. The policy maps state along with goal to the action. So the agent considers states and goal in order to predict the action. There's a technique called hands-on experience replay, which is used for data augmentation in off-policy reinforcement learning. For a set of transition, the reward is recalculated for other subset of goals so that we can augment the data in our replay buffer for different goals, and with fewer transition, with fewer transition, the agents can have more data and can learn faster. Here you can see a description of the proposed algorithm. The technique proposed in this algorithm, the technique that they were proposed in order to improve the performance is in red. The first one is actually using intrinsic reward based on measurement of force sensor, and the second is contact prioritized experience replay, which I will explore in the following slides. Well, another thing is that they add the force, measured force, and the sum of measured force from the beginning of the episode until the time step into the state space, and they use the total measured force from the beginning for the intrinsic reward. Okay. For their setting, they use an sparse reward as extrinsic reward. If the agent were able to put the object in the near the goal, and the difference between the goal space and the position of the object is less than a threshold, the reward is 1, otherwise it's 0. For the intrinsic reward, they use a simple definition. It's an indicator function, and if the sum of the measured force is larger than a threshold, then the intrinsic reward for that state is considered to be 1, otherwise it's considered to be 0. You can see total reward calculated in these equations, and the weights for the extrinsic reward is considered to be 3/4, and for the intrinsic reward is considered to be 1/4 in their simulation for this paper. Here I wanna explain contact prioritized experience replay. Well, the idea behind this technique is to sample instances where the contact is more and it plays more and it has more contact with the object. Here P prime is calculated if the total measured force is less than the threshold, then the instant probability is considered to be 1, otherwise it's considered to be lambda, which is greater than 1. You can see it in this picture. Then the total probability of all instances in the replay buffer is computed. At first, the probability distribution is computed. Then, according to this equation, the probability of episodes are computed, and a mini batch of episodes are sampled. For each episode in the mini batch, they sample n states with this probability actually they sample a time step T prime, and for a time step T which is less than T prime, they sample a transition which consists of a state, goal, action, reward, and the next states. After that, they replace the original goal GAT with the sample states, and for this subset of the goal, they compute the reward and sample the new transition. You can see the simulation setup in here. they simulated the proposed algorithm for 3 different tasks: pick and place, push, and slide. And they adjust the difficulty by increasing the goal space. For example, in the push, the goal space in the blue area is larger, and it's harder for the agents to learn. The difference between the push and the slide area is that in the push, the agent constantly push the object toward the desired goal, and it's do it continually. But in the slide, actually the agent should kick the object to the desired position at once. And the desired position is out of the reach of the robot. For their simulation, they use deep deterministic policy gradient algorithm. You can see here the results. The baseline is using DDPG algorithm with Hinson experience replay. They simulated the results for 5 different random sets, and they take the average. And each epoch is actually 40 training episodes. And the first row is for simple settings. The second row is for medium settings, and the third row is for difficult and hard settings, which the goal state is larger. As you can see, as the settings get harder and harder, the difference between the performance of the baseline and the proposed algorithm increase. And while the baseline fails to learn pick and place and push in the hard settings, the proposed algorithm were able to learn the task quite fast. And finally, for the hard settings, they investigate using different proposed techniques separately. For example, here means using deep deterministic policy gradient algorithm along with in some experience replay, but the state space do not consist the force measurement. Here the dotted blue line means that they add force measurements to the state space. The brown line indicates that they use intrinsic reward alongside with in some experience replay buffer and DDPG algorithm. And the orange line indicates using contact prioritized experience replay instead of in some experience replay, and finally is the total combination of all the techniques. As you can see in the pick and place setting, in the pick and place task, the basic algorithm and DDPG plus here cannot learn the algorithm, but adding the force measurements to the state space, with adding this force measurement to the state space, the performance actually improved. By adding the intrinsic reward, it can learn much faster, but in using other techniques, it does not improve the performance of adding intrinsic reward and DDPG. But for the other tasks, push and slide, it is obvious that using the combination of the techniques which were proposed actually improve the performance of the agent, and it could learn with less time steps. And as a discussion, the proposed techniques actually improve the performance in the simulation, but the thing is that the CPER or contact prioritized experience replay buffer is applicable to off-policy methods. And my main point is that intrinsic reward in this setting is stationary. It means that it does not change with time. As the agent learns and improves the performance, It's actually the same, but in the intrinsic motivation, the intrinsic reward is not stationary and dynamic. For example, consider using prediction error for the intrinsic reward. At first, the prediction error is high, but when the agents explore that area and learns the dynamic of the model, then the intrinsic reward reduced and it's not stationary. So in my belief, I think that we should call it redesigning the reward function. For the future work, the authors proposed simulating in more complex tasks, for example, opening the door. This task is more difficult, and only the force measurement is not enough, and how the force is applied is really more important. They propose investigating the effect of sensor placement in the performance, whether if we change the position of the sensor, does it has any effect on the performance or not. And finally, they could combine this algorithm with learning from demonstration. For example, some trajectory that are suboptimal were given to the agent, and the agent could learn to optimize the policy from those demonstrations so that it could learn faster. Thank you everyone for listening to my talk. Any questions?
Thank you very much, Mohammadreza. So we have plenty of time for questions, I guess. So does anyone have any questions?
Okay.
Hi. So this is Joni. So so in this work they use this force-based intrinsic reward.
Yes.
And I guess if I understood correctly, yeah, it doesn't take into account the progress that you make in learning the policy, so it's stationary. So
Yes.
did they discuss this challenge in the paper, or did they kind of like motivate why they think this is sufficient for the tasks they are doing?
Actually, it is not mentioned in the paper that the intrinsic reward is stationary, and it's my insight. But the idea is that it encourages the agents to have more contact with the agent, and it is rewarded for every time a step that it has contact, it has more contact with the object. So it actually helps the agent to, it's kind of curriculum. The agent learns to have contact with the object, and then it can learn how to complete the task.
I see. So actually what they could do then actually is extend this to more like a curriculum reinforcement learning where
Yes, exactly.
yeah, where they could kind of like explore first this force thing, but then also not care about that anymore when the policy already is able to use the forces correctly. Yeah, okay. Yeah, but this is interesting that it improves the performance. I guess it was pretty significantly in the hard tasks.
Yes, especially in hard tasks where it's important. If the agents learn at first to have contact with the object, and then it would optimize the policy afterward.
Yeah, so this force is kind of like one possible intrinsic reward. This reminds me that you could, for example, create this kind of like a library of many different intrinsic rewards, and then maybe even use curriculum reinforcement learning to control which of those to use for improving the performance.
Yes, it's a great idea using different methods of intrinsic reward along with this kind of intrinsic reward, and actually making a curriculum.
Yeah. That's actually sounds interesting. Yeah. There's a question, I think, in the chat.
Okay. Let's push how to combine demonstration of the sense of life. Okay. For combining learning from demonstration and these methods, we can use algorithms such as, for example, in soft actor critic SAC, there are some methods where they use learning from demonstration. They feel, I think that I cannot remember it total, but I think that in that work they fill the replay buffer with these trajectories and they train the policy at first for some updates, for example, for 2,000 times, for example, and then they optimize. And then after that, the policy was trained on this data. They use online reinforcement learning and they explore it. This is one technique, and I believe that there are other techniques to learn from to enable agents to learn from demonstration, especially in off-policy reinforcement learning.
Yeah, and back to the reward definition. I'm also curious why they defined this like a step function, and why didn't they use this kind of formulation that gradually increases with the size of the force or something like that?
For intrinsic reward or for...
Yeah, for intrinsic. Because at the motivation you said that the motivation was that the challenge is when the reward is sparse, but now I guess that the intrinsic reward is also kind of a sparse reward, right?
Yeah. Actually, they want to show that with using the intrinsic reward only and in a sparse setting, it could improve the performance even if it's sparse. And for it's my insight that they use some of the reward in the episodes so that if the agent has enough contact with the episode from the beginning, if the agent has enough contact from the beginning of the episodes, then it should be rewarded. I mean, they want to not consider the integral of the force, not only the force at this time.
Oh, okay. So this. Oh, okay. So this is a summation.
Yes.
And so if I get, like, for example, the intrinsic reward of +1 at time step 10, and do I get a +1 at the rest of the time steps until termination?
No matter what, no matter if it has enough contact or not, it get the rewards. Actually, I think that it's my insight that if the agent have enough contact, it shouldn't be encouraged to have too much contact with the object. For example, in the slide or in the push tests, for the push test, especially in a slide test, too much contact with the object is not desirable.
Yeah. Interesting.
Okay. Yeah. This sounds like that they want to have kind of like something that's not kind of like reward the amount of force that you get over a certain total amount of force. But I guess you could also smooth this, like make this kind of like a little bit smoother, not to have like a step, but kind of like make it like a smooth curve, but that would still not kind of like get you a lot of reward, even if you increase the force over the kind of like threshold.
Pardon me if you can explain the question.
Yeah, I just meant that so they have this kind of like step function. I don't know if wait, maybe I can can I annotate here? Ah, yeah. So I mean that. Okay, sorry.
Okay.
I mean now they have something like this, but they could also. Oh damn! Why does it smooth this out? Well, anyway, but let's say this is kind of like the step function. Then they could have something like this.
Exactly. This
That's
is
a
the
little
step
bit.
function.
This would be a little bit smoother like this. So that it's not kind of like where here this is kind of like very like a hard threshold.
Yes,
But yeah.
it's even if it's an epsilon greater than the threshold, it would be 1, and a little less than the threshold, it would be 0. And it's not smooth. But I don't know if the reward in the reinforcement learning, there are many tasks that the reward function is not smooth, and it actually works because the gradients is not computed according to the rewards. Am I right?
No, yeah, the gradients are for updating are computed, yeah, according to the rewards, yeah. But I remember there's some paper, also some other work where they use like hard thresholds, and it works in practice better than like this smooth soft threshold.
Yes.
But I don't remember why, or maybe it has not been analyzed very deeply yet. But I have seen also some discussion on this, maybe, yeah.
Yes, perhaps if they shape the intrinsic reward or even the extrinsic reward, so that it's not like the step function and it's more smooth, it might be more beneficial. But I think we, the authors or anyone, should investigate this.
Yeah.
Okay, so are there any other questions or comments? Okay, so we can I guess wrap up the session then. So thank you very much, Mohammadreza, for the interesting presentation, and thanks everyone for joining this session. So we will hopefully see you at the next reading club. Have a nice day.
Thank you. Have a nice day. Thanks.
Bye bye.